Good evening to everyone. I hope I'm audible. So, welcome back to week 5 of the problem solving session for the thermodynamics course. And in this week, we will continue our discussion with pure substances. And in this week, our primary focus will be on ideal gases and understanding how we can deal with some thermodynamic problems, specifically the first law of thermodynamics, and see how we can apply the first law of thermodynamics for a mixture of ideal gases. Okay? So that would be our topic of discussion for this week. And so I think I'll wait for 2 more minutes. Let's see if some students join. Otherwise, we will proceed with our today's discussion. Okay. Yeah. Just a second. I need to do one thing. So. Okay. Okay, sorry, I have to unshare the screen. We'll continue our discussion. So, one more minute, I guess, and then we can start. Okay. Okay, so I think we can start. So, as per our regular agenda, I will briefly go through the concepts that were discussed by Professor Anand in the lectures, and this week I think it is mostly some calculations based on the mole fraction and the mass fraction, and some different equations that are obtained after simplifying those some terminologies. So we will look into that, and it is important because we will use some of those formulas for solving some questions for the similar to the assignments. So there's that. So yeah. So with that, I think yeah, and after that we will directly go into solving some relevant problems for this week's topic. that will be helpful for solving your assignment problems and even in your exams. So with that, let's start. Okay. So Professor Anand mentions that the specific heat ratio gamma, that is gamma is equal to Cp by Cv or Cp bar by Cv bar. Okay, where Cp bar and Cv bar denotes the molar specific heats at constant pressure and constant volume respectively. He mentions that it reduces, the specific ratio reduces with the increase in temperature for air, carbon dioxide and argon, and all of these are considered as an ideal gas, okay, for this scenario. Okay. We know that as mentioned in the previous class, that Cp and Cv, that is the specific heat ratio for the specific heat of gases at constant pressure and constant volume for perfect gases are constants. Okay, they are of constant values, and these type of gases, the perfect gases, are also sometimes known as calorically perfect gases, for which the value of Cp, Cv and gamma are constants. Okay, this is one important point to remember. Okay, but for ideal gases or semi-perfect gases, as mentioned by Professor Anand, this Cp and Cv, that is the specific heats at constant pressure and constant volume, are functions of temperature only. Okay, let me just write it. Functions of temperature only. Okay, so this is the case for an ideal gas. Okay, so you can consider an ideal gas as a special case of gases, and again you can can understand something like these perfect gases to be the further special cases of ideal gases. Okay, and you can see that this both Cp and Cv are functions of temperature only. Okay, so yeah, and this is something similar, so we will leave it for now. So now let us look into mixture of ideal gases. Okay, so this will be the predominant topic of today's discussion. We will try to understand how the mixture of different gases are analyzed thermodynamically, and try to apply the first law of thermodynamics to solve some relevant problems. Okay, so as a precursor to what we are going to discuss today, I will say that all these derivations are thoroughly discussed in the lectures. Okay, so I'm just going to go through them once. Of course, I will try to make you understand as much as I can, but then also if you have any further doubt, you can obviously ask. But if it is still left unclear, because I will just try to explain or reiterate whatever Professor Anand has discussed in the class. But even after, if you have some doubts and confusions, you are always welcome to put those doubts in the discussion forum for this particular course, or you can just post the doubts to me in today's class. I will look into it, reevaluate it, and maybe we can discuss it in the beginning of next week's session. Okay, so let us go through it. Okay, so Professor Anand took a very primal example, that is the mixture of ideal gases. So he considered one of the examples to be air. Okay, and air, as you know, is a predominant composition of nitrogen and oxygen. Okay, and of course the 1% of other gases. But since nitrogen and oxygen, of course in their molecular form, comprise of almost 99% of our air, so we can predominantly consider it to be a mixture of two gases. Okay, like to simplify our calculations, or to understand in the best way possible, we can take a air to be a predominant mixture of nitrogen and oxygen. Okay, there, for example, if in say your numerical problems as well, if the ideal gas is mentioned to be air, okay, and for example for some reason you are not able to recall the molecular mass of air, so you just have to take into consideration the molecular weights of nitrogen and oxygen, take those two into consideration, and then evaluate the mass, the molecular mass of the air with respect to the molecular mass of your nitrogen and oxygen. Okay, so that's what we usually do. Okay, Now let us go through the detailed derivations, where we will get introduced to mole fraction and mass fraction and some different terminologies. Okay, so let us try to just go through them brief, thorough, step by step. Okay, so for example, if this is an example, this is the example of air. Okay, this is the example of air. But for example, now if you consider a mixture of gases, when a mixture of gases which has n number of gases in it, then the total number of moles, that is denoted by small n, would be given by n is equal to n1 plus n2 plus n3 plus dot 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 nn. Okay, where n1, n2 and n3 denotes the number of moles of the respective gases in the mixture. Okay, that's one thing. And so we can represent this summation in a compact manner given by this equation. Okay, the summation of ni, where summation goes from I equal to 1 to n. Okay, that's a very compact way to represent this elaborate summation. Okay. Similarly, if m represents the respective m represents the mass of the mixture, okay, the mass of the mixture, then it should be equal to m1 plus m2 plus m3 plus dot 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 mn, where m1 m2 and m1 m2 m3 represents the mass of the gases, of the respective gases in the mixture. Okay, and similar to the summation of mole fraction, you can represent this elaborate summation in the form of this relation. Okay, the summation of mi I varies from 1 to n. Okay, so this is this is again a very simple generic form that we use to represent summation, but you may know it already, but I thought that it's a good way to introduce you to some terminologies that we are going to use in the rest of the course. Okay, so now comes the definition of this mole fraction and mass fraction. Okay, so by the very terminology you may be able to understand that mole fraction will basically mean that the fraction of moles of the particular gas in the with respect to the total number of moles in the mixture. Okay, so xi represents is popularly used to represent mole fraction in the from the perspective of thermodynamics. So if ni, say if I am dealing with the ith component of the gas, then ni denotes the number of moles of that ith gas. Okay, and so the mole fraction xi will be ni divided by the total number of moles, that is given by summation of nj, j varies from 1 to n. Okay, you can write it I as well, but just to remove confusion, we are using a different index here. Okay, and here the summation of nj will correspond to n from this relation. Okay, so xi will be given by ni by n. Okay, where ni denotes the number of moles of that particular gas. Okay, similarly mass fraction, this is given by yi. Okay, again a popular notation used to represent mass fraction, is given by mi by the summation of total number of summation of mass of the total number of gases in the mixture. Okay, so it is given by mi by m, where summation of mj, j varying from 1 to n is equal to m. Okay, given from this relation. And one more identity would be that the summation of all the mole fractions in the mixture would be equal to 1. Okay, and similarly the summation of all the mass fraction of the gases in the mixture will be equal to 1. Okay, it's something that can be easily understood. Okay, it's not that difficult to visualize. So now coming with the example of our air, so we saw that air is comprised primarily of nitrogen and oxygen. Okay, so let us consider n1 to be the number of moles of nitrogen and n2 be the number of moles of oxygen. Then the total number of moles of gases in the mixture will be n1 plus n2. Okay. Similarly, if we consider m1 to be the mass of nitrogen in the gas and m2 to be the mass of oxygen in the gas, then the total mass of the mixture, that is air, would be m1 plus m2. Okay. Then the respective mole fraction is given by, for nitrogen it is given by x1, that is equal to xn2, that is n1 by n1 plus n2, because we use the n1 index for nitrogen. Similarly for mole fraction, mole fraction fraction of oxygen is given by x2 is equal to n2 by n1 plus n2. Now if you see, if you just sum both of these up, I will just write it. I don't think it's necessary, but still, if you sum both of them up, that is x1 plus x2, you will see that you will get something like n1 by n1 plus n2 plus n2 by n1 plus n2. So n1 plus n2 divided by same denominator, n1 plus n2, is equal to 1. Okay. So similar argument can be made for the mass fractions as well. Y1 will represent m1 by m1 plus m2, and y2 will represent be given by m2 by m1 plus m2. Okay, and you sum, if you sum both of them up, you will see that you will get the total mass fraction of the mixture to be equal to 1. Okay, so this is what it is mentioned here. Okay, it's a generic form of representation. Now we know that now we know that the number of moles in a particular gas is given by let me just write that n is equal to the mass of the gas divided by its molecular mass. Okay, I think I should write it. Just one second. Number of moles is equal to the mass, that is small n, divided by the molecular mass. Okay, then if you just multiply it, this molecular weight, to your the number of moles, you will get that m is equal to n times capital M. Okay, so now for different gases in the mixture, you can write something like m1 is equal to n1 times capital M1, m2 should be equal to n2 times capital M2, mi would be ni times capital Mi, and mn is equal to nn times capital Mn. Okay, nn times capital Mn. So this, because we know that m is equal to m1 plus m2 plus m3 plus mn, then using that identity, if we substitute the values of this in that expression, you will get something like the total mass is equal to summation of mi from I to n would be equal to summation of ni times mi varying from 1 to n. Okay, and how we got this, let us let us look into it. Okay, so it's something like, we know that mi is equal to ni times mi. Okay, from this relation. Okay. Now if we divide this mi by n, this is the total number of moles in the mixture, then ni by mi by small n would be equal to xi by mi. Why? Because this mi by n will be equal to xi. Okay. Similarly, if you now take the ratio of total mass of the gases divided by total number of moles, you will get something like summation of ni by mi divided by n. So now if you consider this division, this summation of ni by n, you will get is something like summation of xi times mi. Okay, so now if you divide both of these terms, you will get mi by m is equal to xi by mi divided by summation of xi times mi. Okay, I hope this is clear. Okay, so that's how we get this relation. Okay, that is yeah, that is yeah, this yi is equal to mi by m, that will be xi by xi times mi divided by xi times mi, that is equal to summation of yeah, this relation. Okay, that's how we get this one. Similar argument can be made for the other following relations as well. Okay, we will see in terms of this mass fraction. Okay, let us go to it. Okay, so now let us consider one scenario. Okay, there's one. These are the what to say, derivations that already have been discussed in the class. But if you have any doubt, we can discuss. Okay, let us try to look into it. Yeah. So let us consider that. Let us represent n1 in terms of your mass fraction and the molecular weight. Okay, so we can see that n1 can be represented as n1 N1 is equal to Y1 by capital M1. That is where M1 is your molecular weight and Y is the mass fraction. Okay, then N2 is Y2 by capital M2. Similarly, Nn is equal to Yn by capital Mn. Okay, and how we are able to write this? Let us look into it. Okay, so for example, if you write N, we know that N1 is equal to small m1 by capital M1. Okay, so now if you just I'm sorry, if you just divide this small m1 by small m, that is the total mass m, then considering that if m is equal to 1, okay, if m is equal to 1, then m1 divided by m will directly give you like m1 divided by m, or m1 divided by 1 will give you m1. Okay, so it's just a simple manipulation. Okay, considering that if m is equal to 1, then we can write n1 to be equal to y1 by capital M1. Okay, so it's just a numerical manipulation used to represent it in that manner. Okay, so that we can get some interesting relations that can be used in a generic manner for a mixture of gases. Okay, so keeping that idea in mind, so we can write something like n is equal to summation of I equal to 1 to capital N Ni. Okay, this part we already discussed. So if N1 is equal to Y1 by M1, then Ni is Yi by Mi. Okay, capital Mi. Then this small n should be equal to summation of Yi by Mi, where summation is from I equal to 1 to n. Okay, so that's how we obtain this. Okay, and now this mass fraction mole fraction xi we know that can be represented as Ni by n. Okay, now since we know that Ni is given by Yi by Mi from this equation, and small n, that is total mole fraction, is given by summation of I equal to 1 to n Yi by Mi, then we can write something like this mole fraction to be equal to Ni by n, or that is equal to Yi by Mi divided by summation of Yj by Mj, where j varies from 1 to n. Okay, so this is again one important relation. Okay, so I think I should just put it in a red box so that you know it's an important relation. Okay, so we'll use this to again obtain one more important relation. Okay, so let us just look into it. Yeah, so let's use this equation. Let us use this equation to find an expression for the molecular weight of a mixture of gas. Okay, because see, if you are dealing with a mixture of gases, then say for example, if you want to say find the total pressure of the mixture, okay, so that say PV is equal to MRT. Okay, then one way or another you'll be dealing with all these terminologies. This P, V, R, T and M as well would be the corresponding properties of the mixture and not the individual gases. Okay, so it's just suitable to be able to represent these parameters in terms of your mixture rather than individual properties. Okay, so it will be a good practice to represent this, to find a way to represent these parameters in terms of the mixture, not the individual properties. Okay, you will see when we discuss one example, of course that was also taken in the class, where we have to find the parameters, corresponding values of the parameters for the mixture rather than the individual gases, because individual gas we already know. So the interesting part is to find the corresponding properties of the mixture. Okay, because see, these molecular weights of some particular gases are known, well known. Okay, but the tricky part is to find the molecular weight of the mixture, which also depends on the individual molecular weights as well as the mass fraction or the mole fraction, whichever way you want to represent. So that's why it's important to know. So one of the important identities that one obtains is that from this relation is that the mass of the mixture, the molecular weight of the mixture, is given by ratio 1 by the summation of Yi by capital Mi. Okay, where summation varies from 1 to n. Okay, so it's a very important equation that we will be using thoroughly, because see, it gives us a very convenient way to find the molecular weight of the mixture in terms of your mass fraction, Yi, because that is something that can be easily evaluated if the mass of the individual gases are given, and the molecular weight of the individual gases. This is something also that is well known. Okay, so it's just a very good what to say way to be able to find the mass fraction of molecular weight of the gas in terms of their individual properties. Okay, so it's a very important relation. So the derivation of this is given here. So how it is obtained is given here, but if you want I can go through it, otherwise you can just go through the notes once I share in the once I share this in the course website. Okay, so okay, if that's okay, then I think I will just skip it for now. You just remember this relation. Okay, but how it is obtained, again it's just a outcome of, let me go back, this equation and some tweaks here and there to obtain that. Okay, okay, so if that's there, then let's proceed further. Okay, so then comes the interesting laws of this mixture of gases. There are two interesting laws. It is, first is the Dalton's law of partial pressure, and second one is the Amagat's law of partial volumes. Okay, where it states that the total pressure of the gas, pressure of the gas exerted by the gases is the summation of the individual pressures exerted from the gases. Okay, similarly the total volume occupied by the gas is the summation of the individual volumes occupied by the gases in the mixture. Okay, so that's something that you need to know, and we will be using this in the problems when you're going to solve. Okay, so let's look into it, how these properties are related to the terms that I have already mentioned. It is the mole fraction and the mass fraction. You will see that there is an explicit relationship between this partial pressure and the mole fraction. Okay, so let us start with our ideal gas law. So we know that PV is equal to nRT, where nR bar T, if you want to deal with your universal gas constant, okay, where R bar represents the universal gas constant. So for the first gas, it will be something like P1V is equal to N1 R bar T. Okay, then P2V is equal to N2 R bar T. Okay, then similarly, if we're dealing with the ith gas, it will be Pi V times Ni R bar T. Now for the entire mixture, okay, for the entire mixture, we know that P1, P2, P3 would be equal to P given by Dalton's law. Okay, Dalton's law of partial pressure. So we can write the ideal gas equation for the entire mixture. This is for a mixture. Okay, so I'll just write it. This is for the mixture. This is for a mixture. Then PV is equal to NR bar T would be the ideal gas for the mixture, where P is the pressure from the mixture, V is the volume of the mixture, N is your number of moles of the mixture, R bar is the R bar is the universal gas constant, that is it will remain constant, but and T is the temperature of the mixture. So these are properties of the mixture. Now if we divide this equation, like these two equations, right, let me show it, these two equations with each other, you will see that you will get something like Ni, like if you just represents in terms of N, the number of moles, Ni will be equal to Pi times V divided by R bar T, and N would be equal to PV by RT. Okay, so you will get, if you divide these two equations, you will get Xi, that is equal to Ni by N, that is equal to Pi by P. Okay, so this relation just explicitly tells us that the partial pressure of a particular gas in a mixture is equal to its mole fraction. Okay, so that's a very important conclusion that we get for ideal gases from the Dalton's law. Okay, so if you follow the similar steps for now considering the specific volumes, you get the Amagat's law, where we get the same conclusion that the specific volume of the volume fraction of a particular gas, it's not a specific volume, actually is a total volume. So volume fraction of a particular gas in the mixture is proportional to its mole, number of moles in the mixture. Okay, So these are the two important conclusions that we get from the Dalton's law and the Amagat's law. Okay, so this is something that you can try to remember. Okay, so now again let us just proceed further with our discussions that we have dealing with our other thermodynamic properties such as your internal energy and enthalpy, because depending upon the process by which the heating is obtained, you will be dealing with either enthalpy or the internal energy change. Okay, so for example, if it's a constant volume process, then the total heat that is in the heat input to the system becomes equal, for ideal gas, becomes equal to your change Cv times delta T, that is basically equal to a change in your internal energy. Similarly, if the process is a constant pressure process, I'm sorry, then the total change or the heat input to the system becomes equal to Cp to delta T, where that is equal to your net enthalpy change. Okay, so these are some important reasons why we are going to deal with your these properties in terms of their individual contributions of the gas in the mixture. Okay, so let U represent the total internal energy of the system. Okay, so we can write something like this is equal to M times U, where M is the total mass of the mixture and U is the total specific internal energy of the mixture. So this can be written something like M1 plus U1 plus M2 plus U2 plus dot Mi Ui plus dot Mn Un. So we can write the internal energy to be the summation of the mass of the respective gases times their respective internal energy. Okay. Similarly, now if you write something like U, that is the specific internal energy, this is equal to capital U by M, then we know that U is summation of Mi Ui, right? So if we do that, then if we consider this Mi Ui divided by M and consider this fraction, then you can write, because this will give you Yi, right? So from that you can write U is equal to summation of Yi Ui, where this is the small u, where summation goes from I equal to 1 to capital N. Okay. Similarly, for enthalpy as well, let's follow the same steps as shown here. You can write H, the specific enthalpy, as H is equal to capital H by M, where capital H is your total enthalpy. Then you can write something like summation of Mi by M times Hi. Then Mi by M is your mass fraction, right? So we can write H to be the summation of Yi times Hi, where the summation goes from I equal to 1 to N. Okay, and just reiterating going back, the detailed derivation of this is again I've added as a separate derivation here, so you can in the next page, so you can just go through it once. Okay, just for your reference. Okay, now I hope it is clear till now. Okay, so now again we represented we dealt with the internal energy in terms of the mass. Now let us discuss it in terms of moles. Okay, it's again a good practice to be familiar with both the approaches, the mass approach and the mole approach. Okay, so with that we can write something like the total internal energy to be the number of moles times the molar specific internal energy. Okay, so this is small u. Okay, I think the notation is a bit confusing. No, sorry, again that's the problem. Okay. This should be small u. Okay, it is actually small u, but sometimes there can be confusions. So similar to the previous case, where in terms of mass we can write it in terms of moles as well. So U would be equal to capital U, its total internal energy, would be equal to N1 times U1 bar, where U1 bar is a molar specific internal energy for the first gas 1. Similarly, you can write N2 U2 bar plus dot Ni Ui bar plus the Nn Un bar. Or if you want to write in a compact manner, you can write capital U is equal to summation of Ni times Ui bar. This is the small u, where the summation varies from I equal to 1 to N. Okay. Similarly, now if you represent this U bar to be capital U by N, okay, okay, that is the molar specific internal energy. So again, this is capital U. Okay, I'm sorry, the representation is sometimes very vague from my end, but I hope it is understandable. Okay, that's why I'm reiterating it each and every term, so that there is no confusion. Okay? So this molar specific internal energy can be represented as the total internal energy divided by total number of moles. Since we know that U is summation of Ni Ui bar, so we can replace it here in this equation. Okay, in this equation, so we can write it Ni Ui bar divided by by n, small n, and Ni by n is equal to Xi, right? That is the mole fraction. Okay, so we can write U bar is equal to summation of Xi Ui bar. Okay, this is for the mixture, and this is in terms of the individual gas components. Okay. Similarly, if you follow the similar steps, you can write H bar is equal to summation of I equal to 1 I equal to 1 to n Xi times Hi. Okay. Similarly, you can do this. Okay. So again, the detailed derivation is given here as well for your reference, because I just want it to be clear. Okay, that's why I kept the detailed derivation. The steps that I skipped for, say, this and let me go back. Sorry. Here as well, I have written it here. Okay, for your reference. Just kindly go through it. So the notes are quite self-sufficient. So you can just refer them. Okay. So now let's. So now till now we have dealt with what? We have dealt with. If I go back, let us try to go back. Okay, so we have dealt with the total. Let me write it. Say different color. What is that? Total internal energy enthalpy. Then the molar specific enthalpy. Total internal energy. Smaller molar specific internal energy. Then we have dealt how to find out your number of moles of the mixture. Okay. Sorry, molecular weight of the mixture. Okay, let me just go back to the notes so that I can get the reference. Yeah, mixture we have dealt with. Let me just go back. Yeah, so I think these are terms that we have dealt with. Okay, see, all these terms that I am mentioning here, okay, are for the mixture. Okay, these are all for the mixture. These are not individual properties. Okay, these are the properties of the mixture, and that's why these are important. Okay, see, the individual properties are easy to find because you already all are one way or another related to the mass and the molecular weight of the individual gas components. Okay, so it is easy to find out, but the interesting property again is the properties of the mixture. Okay, so till now we have found out how to correlate either your mass fraction or the mole fraction with respect to the individual properties, and find out the corresponding properties of the mixture. Okay, so that's what we have done till now. So the only properties that are missing are these: Cp, Cp bar, Cv, and Cv bar. Okay, for the mixture, the specific heats and the molar specific heats of the mixture in terms of, say, the mass fraction and the mole fraction. Okay, so we can write following the similar idea that has been discussed here. Sorry, this will be discussed here. We can write something like Cp bar is equal to summation of Xi times Cpi, and Cv bar equal to summation of Xi Cvi. I think I am making, yeah, it is Cpi bar. Okay, that's why I was confused. Yeah. And similarly, we can also write, let me just write it. Cp, there is specific heat of the mixture as summation of Yi Cpi. Okay, and Cv is equal to summation of Yi Cp, sorry, Cvi. Okay, so now we have got all the necessary properties that we need for the mixture. Okay, so now you may ask, we are still missing the universal gas constant, but again universal gas constant is independent of your mixture of gases or any type of gas, because that's a universal constant. So R bar would be constant for all the cases. Okay, but the thing that will change is your specific uh, gas constant, that is R. Okay, so that will depend on your molecular weight of the mixture. So we saw that for an individual gas, this R is given by R bar by M. Okay, so similarly, if you are say dealing with air, that is itself a mixture of gas, or any specified mixture of gases, then the specific gas constant for a particular mixture would be the universal gas constant divided by the molecular weight of the mixture. Okay, that's it, something that you need to remember. And one more uh, quite obvious observation that you can make is that all the properties that has some mole relation, that is either molar specific internal energy or molar enthalpy, or say the all these properties related to number of moles, we can see that if you are say dealing with a molar specific heat at constant pressure, then you see that it is some way or one way or another related to the number of moles or the moles fraction. Okay, similarly, if you are dealing with the total internal specific heat at constant pressure, you see you are dealing with the mass fraction rather than the mole fraction. Okay, again, it's a very, what to say, it's not like not something that you will not know, but again, it's a good thing to keep in mind so that you don't mix up the signs. Okay, so because in exams you will not go back and recall and deduce this relation from the scratch. Okay, so if you have that in mind, that if you are finding the molar specific heat for the molar specific enthalpy for a mixture of gases, then you can remember that it has to be xi times hi bar. Okay, not yi, because since I am dealing with molar value, so it has to be multiplied with the mole fraction. Okay, so that's something that you can keep in mind for your own benefit. And similarly, again, the gas specific heat ratio can be given by gamma SCP by Cv, that is summation of yi Cpi divided by summation of yi Cvi. Similarly, gamma is again Cp bar by Cv bar, it will be equal to summation of xi Cpi divided by summation of xi Cvi bar. Okay, so again, so till now you more or less had got an idea like what is the main purpose of representing these relations. Okay, so you will see a common trend that all of these relations are one way or another trying to represent the corresponding thermodynamic parameters or properties in terms of the individual gas properties. Okay, so that's the main thing. So that's the main goal that you need to keep in mind. So any problem that you get regarding mixture of gases, your target should be, let me find all the properties of the mixture in terms of the individual gas components. Okay, so now I will wait for say 2 minutes. I will wait for 2 minutes. If you have any doubt, you can put in the chat or you can ask. After that, I will take the 2 problems that was taken by Professor Anand in the lectures. Why I am doing it? Because I feel that these 2 problems are very well equipped to make you understand the concepts in the best way possible. So I will take these 2 problems, go through it, because Professor Anand has already very thoroughly gone through both the problems in the lectures. But still, I think it is a good practice for us to revise whatever we have discussed till now and implement them in solving these 2 problems. Okay, so I'll wait for 2 minutes. If you have any doubt, you can ask. Then I will resume with discussing these problems. So I think we can proceed. So the first problem was regarding this. Okay, let us go through it. A cylinder contains 70 grams of oxygen and 300 grams of helium. The volume of the cylinder is 10 liters. Okay. Calculate the partial pressure and the volume, of course, the partial volume of each gas and the total pressure in the cylinder at 25 degrees Celsius. So that's the question. So right away you can see that you are dealing with terms such as partial pressure and partial volume. Okay, so that basically means that you have to apply the Dalton's law and the Amagat's law and find the partial pressures of the individual gases. Okay, to do that, if you now try to recall that we saw that from Dalton's law we saw that Pi, that is the partial pressure of the ith gas, divided by the P, that is the total pressure of the mixture, is equal to the mole fraction Xi. That's Pi by P is equal to Xi. Okay, so the terms that are missing here are Xi, and if you want to find Pi, the terms they need to focus upon are Xi and P. Okay, both of them are not given. Okay, but what you're being given is the mass of the individual gases and the molecular weights that you need to know. Okay, that's a good practice to know. So that you need to find out, and of course the volume of the cylinder is also given. Okay, that's again a very important clue. Okay, so we know that Pi by P is equal to Xi, and so we can write Pi is equal to Xi times P. So we need to find both Xi and P in order to find Pi. Okay, so let us go through it and see how we can obtain it. Okay, so the primary, again, good way to start with the, since the masses are given, you can find the respective mass fractions. Okay, and because we have a relation to find the molecular weights in terms of our in terms of this mass fractions, so let us start with finding the mass fractions. Okay, so we are given oxygen is equal to mass of oxygen is 70 grams, so it is 0.07 kg, and the mass of the helium is 300 gram or 0.3 kg. Okay, and a good practice is again, I'm sorry, being consistent with the units. Okay, so if you are dealing with say SI units, then keep all your units in SI units. Okay, so good practice. Okay, then volume is 10 liters, so liter I want to deal with meter cube, so let us convert it into meter cube. So 10 liter will be equal to 10 to the minus 2 meter cube. Okay, because 1 liter is 10 to the minus 3 meter cube, or 1 meter cube is 1000 liters. So with that relation we can find this. Okay, and temperature is given to be 298 Kelvin. Now the mass fraction of oxygen is MO2 divided by MO2 plus MHE, that is 0.07 divided by 0.07 plus 0.3, that is 0.18. Okay, and YHE would be just easier way to find 1 minus YO2, that is equal to 1 minus 0.18, that is equal to 0.82. Okay, there's one way to find it, but another way you can also do the same generic step, that is MHE divided by MO2 plus MHE. So 0.3 divided by 0.07 plus 0.3, you will get 0.82. Okay, so the goal is to find PO2 and PHE, that is equal to XO2 times the total pressure of the mixture, and XHE divided by total multiplied by total pressure of the mixture, that is given by the Dalton's law. Okay, now we know that the molecular weight of oxygen is 32 kg per kilomole and molecular weight of hydrogen is 4 kg per kilomole. Okay, then from this relation I already boxed it and also gave how to derive it. So you can kindly go through the notes, and also in the lectures also Professor Anand has discussed it, so you can refer any one of them. Okay, so the molecular weight of the mixture is given by 1 by summation of yi divided by mi. Okay, so all these terms you already have, that is YO2 we know, YHE we know, MO2 we know, MHE we know. So you can easily find the M mix, that is 1 by 0.18 divided by 32 plus 0.82 divided by 4. So if you do that, you will get the molecular weight of the mixture to be 4.74 kg per kilomole. Okay. Now we know that, I will tell you how we got here. Okay. We know that xi is equal to ni by n, and from the notes, if you go back, I don't want to scroll back that further back. So from notes, if you recall, you will get xi is equal to yi by mi divided by summation of yj by mj, where j goes from 0 to 1 to n. Okay, so that's one relation. From here, since we know that, since we know that m mix is equal to 1 by summation of yi by mi, so from that we can write xi to be equal to yi by mi times m mix. Okay, because it is basically yi by mi times 1 by yj by mj. Okay, so this is equal to m mix, right? So we can write xi is equal to yi by mi times m mix. Okay, I already mentioned here. So xO2 would be YO2 divided by MO2, this is 0.18 divided by 32 times 4.76. Now you see why we need the molecular weight of the mixture. Okay, from that you get xO2 to be equal to 0.026. Okay, similarly you can again just simply do 1 minus 0.026 to find xHe, but again you can use this formula as well. So xHe would be 0.82 divided by 4 times 4.76 or 0.974. Okay, so now you got both xO2 and xHe. Okay, so now the thing is, you need, since you have already got the mole fractions, the next thing to find the partial pressures is to find the total pressure of the mixture. Okay, so for that I think we can again resort back to your ideal gas law. Okay, but meanwhile they also asked us to find the volume of the partial volume of the the individual gas components. Okay, so since we already know the mole fraction and we know the total volume of the gas, okay, that is 10 to the minus 2 meter cube. So from that we can easily find the partial volume of oxygen to be 10 liter times 0.026 or 0.26 liter, or the partial volume of helium to be 10 liters times 0.974 or 9.74 liter. Okay, that's we obtained from the Amagat's law. Now we need the pressure. Okay, so using the ideal gas law for the mixture, okay, again iterating for a mixture of gases, we can write P mix times V mix is equal to M mix times R mix times T mix. Okay, or P mix is equal to M mix divided by the universal gas constant R mix divided by, again, capital M mix, the molecular weight of the mixture, times P mix divided by V mix. Okay, so V is taken here. Okay, and R I have represented as R bar by M. Okay, so now if you substitute the value of all these things in this equation, okay, M mix you already know it's 70 grams plus 300 grams or 370 grams, so 0.37 kg. Okay, so we substitute all these values here. 0.37 times R bar is 8.314 in terms of kilojoule per kg per kilomole, then kg per kilomole. Okay, then it is 4.74 your molecular weight of the mixture. Okay, then T is 298 as given in the question, or as given in the question. Okay, and the volume is 10 to the power minus 2. Okay, that's why we need to keep in SI units, because all our terms we are keeping in SI units. Okay, just 1 second. Just 1 second. Yeah. From that, from that you get that the mixture, the pressure of the total mixture is 193 bar or 19.3 megapascal. Okay, if you just do this calculation, you will get this 19.3 megapascal. And since we got the mole fraction and the total pressure, we can easily find out the partial pressure of oxygen, that is xO2 times P mix, or 0.026 times 19.3 or 0.5018 megapascal, and PHE to be Xe times P mix, or 0.974 times 19.3, or 18.7982 megapascal. Okay, so that's how we do it. Okay. So let us go to the next question. Okay. Consider, and I hope this example was clear. So if there is any doubt, you can ask, or you can write in the chat box as well. I hope then it is clear. Then I think we can proceed uh, further. Okay. So let us look into the next question. Consider an just 1 second. Okay, just 1 second. Just 1 second. Just 1 second. So the question is, consider an ideal gas mixture of 1 kilomole of hydrogen and 1 kilomole of nitrogen. Okay. Find the mass fractions and the mole fractions of hydrogen and nitrogen. Also find the molecular weight, specific gas constant R, and the specific heat Cp and Cv of the mixture. Okay, see, everything is coming back, like why we had to do all those derivations, because they are asking you to find the properties for the mixture rather than the individual properties. Okay, individual you can easily find, so they are asking you to find the properties of the mixture. Okay, so that's why it's important to know how to find these from the individual gas components. Okay, now if this mixture is heated from an initial temperature of 300 Kelvin to a final temperature of 400 Kelvin at constant pressure, again that's a very important uh, term, that at constant pressure. Okay, you will see why. Find the change in internal energy delta U, change in the enthalpy, specific enthalpy delta H, Q and W of the process. Okay, so this it's a combination of the properties of ideal gas as well as the first law of thermodynamics. That first you need to find the properties of a mixture, and then given the process has been mentioned, that is heated at a constant pressure from 300 to 400 Kelvin, you need to apply the first law of thermodynamics to find the change in the net heat, to find the net heat input and the net work output. Okay, or the net heat and the work interactions. Okay, that's what the question is. Okay, and you can see this question is again a kind of inverse of the previous problem, where you were given the mass of the gases rather than the mole, number of moles, and you were asked to find the mole fraction. Because from now here you can easily find the mole fraction, but mass fraction you need to find using the identities that we have discussed. Okay, so let us try to look into it. Okay, so we have, and again I'm sorry for this beeping sound. So it's outside my room, so there is a beeping sound, some alarm, so it's beeping quite violently. Please, sorry for this inconvenience. It's shut down now. Okay, so we can proceed. So the number of moles of hydrogen is 1 kilomole, number of moles of nitrogen is 1 kilomole. Okay, so the mole fraction of hydrogen would be 0.5 and the mole fraction of nitrogen would be 0.5. Why? Because since these two are equal, the respective mole fraction of the individual gases with respect to the number of moles in the gases would be half of it. Okay, half of the total moles. Okay, or you can do it like this as well. It's fine. We know that the molecular weight of hydrogen is 2 and the molecular weight of nitrogen is 28. Okay, not to get confused with the atomic weight, because atomic weight of hydrogen was of course 1, but since we are dealing with hydrogen molecule which exists in H2 form, that's why its molecular weight is 2. Okay. So the primary task of the question is to find these properties. Okay, the mole fraction, the mass fraction, the specific ratio, sorry, the specific gas constant and the heat ratios of the mixture. Okay. So from this relation again, that we dealt in the previous problem also, xi, let me just write it. Xi will be equal to yi by capital Mi times M mix. Okay, the M of total molecular weight of the mixture. So we need to find the individual mass fractions. Okay, that is yi. So we already know Mi and xi. So the other thing that we do not know right now is M mix. Okay, let us now try to find M mix. We know that the molecular weight of the mixture can be given by summation of xi times Mi. Okay, so we know xi is 0.5 times the molecular weight of hydrogen plus plus the number of moles of the mole fraction of nitrogen is 0.5 times the molecular weight of nitrogen, 28. If you do that, you will get M mix as 15 kg per kilomole. Okay. So now with M mix in our hand, now we can directly attack this relation to find yi. Okay. So YH2 would be XH2 times MH2 divided by M mix, where XH2 is 0.5 and MH2 is 2. Okay, and divided by M mix is 15. If you do that, you will get YH2 as 0.066. Okay, you can find YN2 as simply as YN2 would be 1 minus 0.066. Otherwise, you can also follow these steps as well, but you will get similar result. It is YN2 is 0.934. Okay. I hope this is clear till now. Okay. So now we can find the specific gas constant for the mixture. Okay. So similar to the previous properties, we can find R mix to be summation of yi times Ri, or R mix to be the R bar divided by M mix. Okay, both of these are fine. Both of these are perfectly fine. Okay, but we can do either of them because we have yi for individual gas components, and the thing would be to find the specific gas constants for hydrogen and nitrogen. So that you need to evaluate. But since we can skip this by using this formula, so let us do that. Okay. So if you do that, R mix would be 8314.5 divided by 15. That would be equal to 554.3 joule per kg Kelvin. Okay. So if you do this as well, you will get the same result. Okay. Next is to find Cp and Cv. Okay, for the mixture. Okay. So if you recall, Cp for the mixture in terms of your mass fraction would be given by the summation of yi Cpi, and of course Cv would be summation of yi Cvi. Okay. Then let us start with our and again Cp mixture, Cp bar mix would be xi by Cpi, and Cv mix, I think I can write it directly. Cv mixture would be summation of xi Cvi. Okay. Just 1 second. Yeah, it has to be a bar here. So we know that Cp is gamma r by gamma minus 1. So this we have already derived in the last class, so I'm not going to derive it again. Okay. Or Cp bar is gamma r bar by gamma minus 1. Similarly, Cv would be r by gamma minus 1, or Cv bar would be r bar by gamma minus 1. Okay. Sorry. Now for hydrogen, if you want to say use this relation, okay, where is it? If you you want to use this relation, then you need to uh, you need to find the specific gas constant for hydrogen. Okay, so we know R would be R bar by M, where M is the molecular weight. So for hydrogen it would be R bar by the molecular weight of hydrogen, or 8314.5 divided by 2, or 4157.25 joule per kg Kelvin. Okay, so if you substitute the value of R here for hydrogen, we will get CpH2s 1.4 times 4157.25 divided by 1.4 minus 1, that will be equal to 14.55 kilojoule per kg Kelvin. Okay, so now you may ask why gamma is 1.4. So since we are dealing with diatomic gases, both hydrogen and what's the other gas? I'm sorry, hydrogen and nitrogen. Okay, so since both are in diatomic form, so the specific heat ratio would be 1.4. If it is monoatomic, again it was 1.67. Okay, depending on the degree of freedom. If you recall from the notes, you can know D plus 2 by D was the specific heat ratio, right? Then Cv of hydrogen would be Cph2 minus R, because we know that Cp minus Cv equal to R, or Cv would be Cp minus R. Okay, so Cph2 would be Cph2 minus R, or 14550 minus 4157.25, or Cvh2 would be 10393 joule per kg Kelvin, or 10.393 joule per kg Kelvin. One way to rectify whether your answer is correct or not is to just see the values, that Cp always has to be greater than your Cv, okay, for these gases. Now similarly we can follow the exact same steps for nitrogen. Okay, so Cp nitrogen would be 1.4 times your R. The specific heat ratio for nitrogen would be 8314.5 divided by just 1 second, it should be 28, right? I'm sorry. Sorry. No, nitrogen would be 14 only, right? If I'm not wrong. No, it's 28. Yeah, of course. Atomic weight is 14. It should be 28. See, this again, I also am not quite well versed, so it's a good practice if you are well versed with these values. Let me just check whether this changes the values or not. Okay, sorry for the confusion. Just wait for 1 second. It is 28. Okay, sorry for the confusion in the notes. It should be 28, and the value is consistent. The result, I just mistakenly wrote it 14. It should be 28. Okay, so this 297. If you do that, you will get this to be 297 joule per kg Kelvin, or 0.297 kilojoule per kg Kelvin. Okay, so Cpn2 will turn out to be 1.0395 kilojoule per kg Kelvin. Okay, again Cpn2 can be evaluated from the similar steps. Cpn2 is 1039.5, 1.039 minus 0.297, or Cvn2 is 0.7425 kilojoule per kg Kelvin. Okay, so one more good, I would say, interesting observation would be, you can see that the specific the values of the specific heat ratios and the specific gas constant for nitrogen are quite similar to the air. Okay, for air, R air is 0.287, Cp air is 1.005, and Cv air is 0.718. So since nitrogen has the highest composition, or highest has the highest, what to say, has the highest composition in the gas, in the air. That's why the specific heat of the air is also similar to nitrogen. Okay, again, it's just the interesting observation that I saw. That's why I mentioned. But that's why it's happening. Okay, so for example, if you have a gas, for example, say which has 99% of nitrogen and 1% of hydrogen, okay, for example, then if you know the molecular properties of nitrogen, then you can easily approximate the properties of a mixture to be almost similar to be of nitrogen. Okay, so that's again one of the quick ways to uh, evaluate the mixture of gas if the composition of one of the gas is very high. Okay, so yeah, so from that we need to find the specific heat ratio and the molar specific heat ratios. Okay, so again we can simply use the identities. That is, Cp mix would be summation of yi Cpi, and Cp bar mix would be summation of xi and Cpi bar. So Cp mix would be 0.066 because yi we already found out, times 14.550 plus 0.934 times 1.0395, or Cp mix would be 1.9312 kilojoule per kg Kelvin. Similarly, Cp bar mix would be summation of xi Cpi bar, so it is 0.5 times 29.1 plus 0.5 times 29.1. Okay, because Cp I'm sorry, and then Cp mix can be found out as 29.1 kilojoule per kilomole Kelvin. Okay, the other way to find the Cp bar mix would be finding out gamma R bar by gamma minus 1. So 1.4 times 831.5 divided by 1.4 minus 1. If you do that, you can again get the same results. Okay, it is same. Okay. Similarly, Cp mix can also be found out as Cp bar mixed by the molecular weight of the mixture, 29.1 by 15, that is 1.94. It's almost similar to this. Okay, so there are different ways to find out these values. Whichever you find suitable, you can do. Okay, there is no issues. So Cv mix would be Cp mix minus R. So it is 1.94 minus 0.5543. So R, if you recall, was, if I go back, R we evaluated, right? Sorry, okay, it's a long problem, so I'm just, this R mixture was 0.5543 kilojoule per kg Kelvin. Okay, so from that you get Cv mix to be Cp mix minus R, or 1.94 minus 0.5543, or 1.3857. Okay, so all the terms that was required to be found are already found. Okay, so now the question was, the heating was done at a constant pressure process from 300 to 400 Kelvin. Okay, so Q would be mCp mix delta T. See, it's a constant pressure heating, okay, for an ideal gas, so that should be equal to the net change in the enthalpy. Okay, so this mCp mix times delta T, or m delta H, and the change in the internal energy would be m times delta U, or mCv mix delta T. Okay, this is valid for ideal gas only. Okay, and work done would be, for the first law, the net heat interaction minus the change in the internal energy. Okay, now since we are dealing with the mass of the system, then we need to find the total mass of the mixture, which can be easily found out from the mass of the individual gases. Okay, since we know that, let me go again use this expression, that number of moles is equal to the total mass, the mass divided by the molecular weight. Okay, so mass of the gas would be number of moles of the gas times its molecular weight. Okay, now using that identity, you can find out mH2 to be, number of moles was 1 kilomole times the molecular weight, so we get mH2 to be 2 kg. Similarly, the mass of nitrogen in the gas would be nN2 divided times mN2, so 1 kilomole times 28, or 28 kg. Okay, so total weight of the mixture would be 30 kg, that is mH2 plus mN2, or 30 kg. Okay, so the net heat transfer Q would be m mix times Cp mix times delta T, that is 30 times 1.94, Cp mix was 1.94. If you go back here, yes, it's 1.94 times delta T, that is 100. So we get Q is 5820 kilojoules, positive because heat is increasing, temperature is increasing, so heat input to the system. Similarly, delta U would be M mix Cv mix times delta T, where M mix is 30, Cv mix is 1.3857 times 100 or 4157.1 kilojoules. Work done would be this from the first law, Q minus delta U, or 5820 minus 4157.1, that is equal to 1662.9 kilojoules. Okay. So that's what we are asked to find, and we found out. Again, it's a very nice, quite involving problem that touches upon all the derivations and concepts that we discussed in the class. So both of these problems were, I felt, was very, very helpful and useful, and helpful and intuitively very, what to say, helpful for the students to understand the concepts. Okay. So again, I will wait here for say 2 minutes. So if you have any doubt, you can ask. Otherwise, I'll just touch upon the last part of the discussion that was taken by Professor Anand. I'll skip one topic because I think that it's a very theoretically heavy topic. So you can discuss that. You can read that from the lectures. And since there were no relevant problems to that from that topic, at least with respect to the assignment, I thought I will skip that part. But of course, if you're interested, you can proceed. Okay. So I think let's just try to finish this session, if not drag the session as much. So I will just go to it. Okay. So we know that for ideal gases, the governing equation is the ideal gas law is PV is equal to MRT. Okay. Now, if we divide the volume by the mass, it becomes your specific volume. Then we can write it as PV is equal to RT. Okay. Now, since if we consider an isothermal process, that is a constant temperature process, then then all the terms in your right hand side is R and T becomes a constant. Okay, because R is itself a constant, right, for a particular gas, and T is constant for a isothermal process. Then in a PV plot, the constant temperature lines are hyperbolic. Okay, why? Because you see that for constant temperatures we get a relation that is PV is equal to constant. Okay, so the PV plot will give you constant temperature lines, that is the isotherms, where this would represent a rectangular hyperbola. Why? Because see, if we consider in a xy plot, xy times x times y is equal to c gives a rectangular hyperbola. So with that analogy, in a PV plot, PV is equal to some constant will give you a rectangular hyperbola. So all these isotherms are rectangular hyperbolas. Okay, so the detail, again, I am trying to not dive deep into it, but again, it was discussed in the lectures, but I think this is more than enough. Okay. Similarly, now if we consider if we look into the TV plot now, the temperature volume plot, for an ideal gas, we get that T is equal to PR by V. Okay, again from this relation, T is equal to PR by V. PR times V. I'm sorry, P by R times V. Okay. Now you see that if this pressure is constant, okay, if this pressure is constant, then the coefficient of the specific volume V becomes a constant. Okay, so we can write something like T is equal to C times V. Okay, so we see that from this equation we can say that this temperature volume plot, in a temperature specific volume plot, the lines of constant pressure or the isobars would be straight lines, because this is an equation of straight line. Okay. And one more important thing to note here is that for this, even though there is a equation of these are equations of straight lines, the slope of these lines depend on the particular value of P. That is, there can be several isobars. So as the pressure increases, that is, say initially it was 500 kilopascal, then we are dealing with high isobar of 1000 kilopascal. You can see that the slope of these lines are also increasing because these are directly proportional to pressure. Okay, so if the slope is directly proportional to the pressure, right? So if pressure increases, the slope of the curve also increases. Okay. So again, these are some uh, trivial, not, I will not say trivial, very simple concepts, but these may come as some 1 mark questions in your assignments or even your exams or other competitive exams. Okay, what's the property, what's the characteristic of isobars in a TV plot? Okay, someone may ask. Okay, so these are straight lines where the slope varies with the values of the pressure. Okay, now again, if we look into these again, I will just go to them very quickly. Again, sir discussed it, that's why I am mentioning it. That for calorically perfect gases, Cp minus Cv is equal to R, that is a constant value, and Cp and Cv themselves are constants. Okay, so that's one thing to uh, remember. Okay. And then for ideal gases, Cp and Cp minus Cv is still equal to R, but Cp and Cv are functions of time. Okay, so that's why they have a variation with respect to time, and you see that the difference between Cp and Cv is equal to R. Okay, so they have similar trend of variation, but Cp is greater than Cv with a factor of R. Okay, so I'm not going to dive deep into it. These are theoretical concepts, so this can be, again, there's nothing more that I can discuss about it. So if you have any doubt or you want to look more into it, you can just go to the lectures, okay, for your reference, or follow the textbook as referred by Professor Anand. Okay, so one other final topic was the compressibility factor. So there was a separate lecture upon it, so I just touched upon the plot and it's shown here, and for my convenience I think that since there are no relevant questions upon this concept in the assignment, so I'm not diving deep into it, but again, for reference, you can go to the elaborate discussion upon it that was taken in the lecture. Okay, so sir mentions that there is a compressibility factor for these actual gases compared to an ideal gas, that PV actual by RT. Okay, so that's PV actual divided by RT gives you the compressibility factor. So for an ideal gas, PV by RT will give you a constant value, right? So if this varies, it will vary for an actual gas. Okay, so this compressibility factor is a measure of deviation from the ideal gas. Okay, and sir discussed this through different elaborate plots, so it's a very good way to look upon them. So I will suggest that you can maybe look into the lectures for your better understanding. Okay, and yeah, so that's all. So let us go to the questions for this week's discussion. Okay, so since the since the number of participants for today's class is not that much, so I think I will, for saving time for both us and the students, what I will do is I will go through each and every question once. I'll give you say 1 minute or 2 minutes if it's not that elaborate, and then we can try to look into the solution. Okay, so the first question is, which of the following is the correct statement for Dalton's law of partial pressures? Okay, first is the pressure of a gas mixture is equal to the sum of the pressures each gas would exert if it existed alone at the mixture temperature and any arbitrary volume. Okay, second is the pressure of the gas is equal to the sum of the pressures each gas would exert if it existed alone at the mixture temperature and volume. Okay, the mixture temperature and mixture volume. Okay, third is pressure of a gas mixture is equal to the sum of pressures of each gas that would exert if it exists alone at any temperature and volume. Okay, finally is none of the above. Okay, so you can just try it out. I will give you say 1 minute to look into it. We already looked upon the governing equations and how the Dalton's law of partial pressure was derived, so you can tell me the correct option. Okay, okay, so okay, say take some more time. Yeah. So if you if you look into it, we saw something like PVI, sorry, PIV was equal to RB. Yeah, exactly. That's correct. Yeah, that's correct. That's what I wanted to show. That's correct. Thank you. So the volume and the temperature has to be the mixture temperature and volume. Okay, so that's why I wanted to, I'm sorry, discuss that. Okay. So yeah, or something like PIV is equal to MIRT, or PIV is equal to MI, sorry, NI R bar T. Okay. So B is the correct option. So let's look in the next question. It is a cold sunny day in Merrill, Wisconsin. The temperature is minus 10 Fahrenheit. The barometric pressure is 100 kilopascal. Estimate the outside air density. Okay. And also estimate the molar density N by V of the air. Okay. So this question is quite simple. It's just a transformation of the temperature scales from Fahrenheit to Kelvin. You can look into internet for the reference, like how to convert from Fahrenheit scale to Kelvin scale. Pressure is known, right? So air also, you know the molecular weight. So from that you can find the density. Okay. It's not that complicated. So I think I can discuss this one. It's just a temperature scale transformation. So yeah. So the thing was to convert the temperature to Kelvin scale. Okay, because all of these calculations that we do in the classical thermodynamics perspective, we do it in the Kelvin scale. Okay. So T here at Kelvin will be given in terms of the Fahrenheit, will be given by as 5 by 9 times T here at the Fahrenheit scale plus 459.67. So T here at the Fahrenheit scale is 10, so minus 10. So T here at Kelvin scale will be 5 by 9 times minus 10 plus 459.67, or T here at Kelvin scale would be 249.8 Kelvin. Okay. Now density is given from the ideal gas law. PV is equal to MRT, or M by V is rho, so rho is equal to P by RT. Okay. So from that, P is 100 kilopascal divided by R is 287 for air, and temperature is 249.8. So that becomes rho becomes equal to 1.395 kg per meter cube. So the molar density was given a number of moles per unit volume. So number of moles is N by V, or N is M, small m by capital M by V, or M by V is again your density rho, so rho by M. So rho is 1.395 kg per meter cube, and density is 28.97 for air. So from that you get the molar density, that's at capital N by V, to be equal to 0.048 kilomole per meter cube. Okay. Yeah, there is an interesting derivation that has to be made. So this we will discuss thoroughly when we discuss about the entropy, or the second law of thermodynamics. But still I feel this question is relevant for you, because when we'll start discussing about the next week's part, that is the steam, the properties of steam from the perspective of pure substances, there the TS plots become we introduce the TS plots. So I think it's a good, what to say, a good way to introduce you to the concept of this entropy, or at least in a generic way. Okay, not the specifics or not in detail, but what entropy is, like just a very slight, what to say, introduction. Okay, so the question is, Show that for an ideal gas, the slope of the constant volume process line on a TS diagram is more than the constant pressure line. Okay, constant pressure process line. Okay. So this question, I think it's difficult to what to say, expect from students to tell the answer because it is a proof. Okay. So for that, I think we can do it together. Okay. So let us look into it. Yeah. For 1 kg of gas, just go. Okay. Sorry, just go with me through the derivations. Okay. So if there's any doubt, you can ask. Okay. So for 1 kg of gas, the first law of thermodynamics is given for a thermodynamic process is given by dq is equal to du plus pdv. Okay. Now the definition of entropy or quantifying by way the entropy is quantified is for a reversible process, the change in entropy ds is equal to actually del q by t, or del q becomes equal to tds. Okay, equal to tds. Okay. This how entropy is quantified for a reversible process. Okay, for a reversible process, then d delta q becomes equal to tds equal to du plus pdv. The other terms become remain same. Okay. Now du becomes cv times delta t for an ideal gas. Okay, and plus pdv, tds equal to cv dt plus pdv. Okay. Now we can write cv dt as tds minus pdv. Take pdv in the left hand side. Just simple change of signs. Then if we divide all the terms by cv, you will get dt as t by cv ds minus p by cv dv. Okay, that's equation number 1. Now there's one more interesting thing to know is that any thermodynamic property, if they're in equilibrium state, can be represented in terms of 2 other thermodynamic properties. Okay. So T can be, since we are dealing with C, the logic is that we need to find a change in temperature, and for that you need to find its slope. Okay, so that the main motto is how to represent it in terms of how to represent the slope in terms of these parameters. Okay, these coefficients. So dt is the change in temperature, and you see the other 2 parameters that are changing are the entropy and your specific volume. So let us represent T in terms of the entropy and the specific volume. Okay, you will see why this becomes relevant. So dt would be equal to dou T by dou S ds plus dou T by dou V times dV. It's a very fundamental definition of the differential. Okay, the complete differential represented in terms of partial differentials. Okay. Or I just use something like dx is equal, dz is equal to dou z by dou x dx plus dou z by dou y dy, where z is a function of x and y. So this is the identity I've used here. Okay. So for constant volume process, dt becomes equal to dou t by dou s times ds. Okay, so again from equation 1 and 2, then you can see that because this will be equal to 0 for a constant volume process, right, and this will also be equal to 0. So from these 2 relations you can say that dou t by dou s at constant volume process is equal to t by cv. Okay, just comparing the coefficients of ds. Okay, that's the first thing. Okay, so let us give it equation number 3. Similarly, for an we can write from definition of enthalpy, we can write TDS is equal to ds minus VDP. Okay, so let me give you a task. Find out how I wrote it. Okay, hint clue is I started from H is equal to U plus PV. Okay, starting with this relation for a constant pressure. Starting from this relation, tell me how I found this out. Okay, I got TDS is equal to ds minus VDP. Okay, or dH is equal to Cp dt, because dH, the change in enthalpy for an ideal gas is Cp times dt. Okay, so TDS is equal to Cp dt minus VDP, or Cp dt is equal to TDS plus VDP, or dt is T by Cp times ds plus V by Cp times dP. Give it equation number 4. Now again using the same concept that we used here, here now since the parameters that are changing are ds and dp, so let me represent the temperature in terms of the entropy and the pressure. So dt would be dou t by dou s ds plus dou t by dou p dp. Now if for a constant pressure process, this would be equal to 0, this would be equal to 0. So from equation 4 and 5, if you compare the coefficients, you will get dou t by dou s p would be equal to t by cp. Okay, equation number 6. So now if I go, we know that cp is always greater than cv for an ideal gas. So t by cp should be less than t by cv. This is equation number 7. So from equation 3, 6 and 7, you can write that dou t by dou s v is greater than dou t by dou s p. Okay. So in a TS plot, the constant volume process lines has a greater slope than the constant pressure process lines. So that's how we get the conclusion. Okay. I hope this was clear. Again, it's something quite new because we are getting introduced to the concept of entropy, but this is how we try to introduce you with new concepts. Okay, and elaborate discussion upon entropy would be when we discuss the second law of thermodynamics. Okay, so yeah. So next question is, an ideal gas is contained in a container which occupies a volume of 1000 centimeter cube at 25 degrees Celsius and 1 atm. Calculate the number of molecules of gas in the container. Okay, so here again the approach would be to find the number of moles of the gas, right? Then say if you know the number of moles, then just multiply with the Avogadro's number to find the total number of molecules. Okay, so that's how we can approach the problem. So you can know you can use this equation, that is PV is equal to N sorry PV is equal to N R bar T. So N will be equal to PV by R bar T. You simply use this, you know you have P, V and T, and R you already know is a universal gas constant. You can find the number of moles. The number of molecules would be number of moles times the Avogadro's number. Okay. So Avogadro's number is again a constant value. So if you do that, you get something like N is equal to PV by R bar T, or 101325 times 100 times 10 to the minus 6. This is converting into meter cube. Okay, the volume, and R is 831.5 times 298 is 200 degrees Celsius in terms of Kelvin. Okay, always change the temperature to Kelvin scale for this kind of calculations. Okay, the number of moles turns out to be 4.089 into 10 to the minus 6 kilomoles. Okay, so number of molecules of the gas is given by the Avogadro's number times your number of moles of the gas. So Avogadro's number is given by 6.023 into 10 to the power 23, so 6.022 into 10 to the power 23 mole inverse. Okay, so to cancel out these two, we need to transform this in terms of moles. So this becomes, since it is in terms of kilomole, we need to multiply it with 10 to the power 3 to make it in terms of moles, right? So we get this to be equal to 4.089 to 10 to the power minus 3 moles. So this mole will cancel out. So we get number of molecules to be 2.462 into 10 to the power 21 molecules. Okay. So next question is, the graphs of specific enthalpy and internal energy versus temperature for an ideal gas must be straight lines. True or false? Yes, exactly, because it can either be straight lines or curved lines as well, as discussed by Professor Anand. Okay, so it is false. Let us look in the next question. For a perfect gas, Cp and Cv are constant functions of temperature only, function of temperature and pressure, and yeah, A exactly. So these are constants. Okay. So final question is, which of the following has been matched correctly? Boyle's law, or like this, which of the following options are matched correctly? Okay, these. Just look into it. You know the Boyle's law, Charles' law, and Gay-Lussac's law. So are they? Which of the options are matched correctly? Exactly. So since I'm sorry, Boyle's law is PV is equal to constant, Charles' law is V by T is equal to constant, and Gay-Lussac law is P by T is equal to constant. So since none of them are matched correctly, so the option is E. Okay. So yeah, so that's all from my end today. So if you have any doubt, you can ask. Otherwise, we can meet in next week's session. Is there any doubt? Otherwise, we can close the session and meet next week. Okay then. So let's all meet next week. Okay. Thank you for attending the session. Yeah. Thank you. Thank you. Thank you so much.